Welcome. My name is Jesse Fosheim, and today I will be discussing efforts at the Colorado School of Mines investigating incorporating narrow-channel fluidized beds into counterflow particle SiO2 heat exchangers for particle-based thermal energy storage in next-generation CSP plants. Particle-based thermal energy storage offers arguably the most feasible near-term solution for coupling CSP to high-efficiency SiO2 power cycles that operate at temperatures in excess of 700 degrees Celsius. Engineered alumina silica particles are inexpensive, mechanically robust, chemically inert and non-corrosive, and offer a wide operating temperature range. Here, I show a schematic of a solar-driven SiO2 power plant with particle-based thermal energy storage. On the left, solar heat is stored in particles as they pass through a particle receiver. The heated particles feed the hot side of a particle SiO2 heat exchanger, where the solar heat is transferred to the SiO2 working fluid that drives the Brayton power cycle, like that shown on the right. The cooled particles are then stored and recycled back to the particle receiver. Of the subsystems necessary for implementing particle-based thermal energy storage, the particle receiver has received the most attention, with some prominent examples shown on the right. On the other hand, the particle SiO2 heat exchanger, which similarly represents one of the most important components of the thermal energy storage subsystem, has not received the same level of attention and therefore comprises one of the primary risks and uncertainties for scale-up and commercial implementation of particle-based thermal energy storage. Current designs for particle SiO2 heat exchangers rely on moving packed beds, where particles flow through narrow vertical channels and transfer heat to the SiO2 by sliding contact with the confining walls. While the SiO2 flow provides effective heat transfer, particle side heat transfer is limited fundamentally by the low effective thermal conductivity of the bed, resulting in effective particle wall heat transfer coefficients generally less than 300 watts per meter squared Kelvin. These designs therefore require short conduction length scales on the order of only a few millimeters and result in large heat exchangers that do not readily meet the Department of Energy cost targets for next-generation CSP plants. Prior work at Mines has demonstrated that significantly higher particle wall heat transfer coefficients in excess of 1,000 watts per meter squared Kelvin can be achieved in small narrow-channel fluidized beds, suggesting that this approach could enable smaller, more cost-effective heat exchangers for particle-based thermal energy storage. Towards that goal, we established the new larger-scale narrow-channel fluidized bed experimental facility. The bed is 18 meters deep, multiple times larger than those required for moving packed beds. During operation, preheated particles are gravity-fed into the top of the channel and are fluidized by air injected at the bottom of the bed. The particles progress steadily in a net downward path and exit through a controlled orifice gate at the bottom. The fluidized gas is separated from the particles through a porous media as it exits at the top of the channel. This facility is modular with interchangeable walls. The facility is shown here, configured for low temperature operation with flow visualization. The back wall is instrumented with thermocouples embedded in the internal and external surfaces. For high temperature tests, the window is replaced with an identical instrumented wall. External heating is provided through the wall by an array of quartz lamps. Alternatively, both walls can be replaced with air-cooled microchannel plates to simulate forced cooling by SiO2. Thermocouples to the side of the channel measure bulk bed temperatures, and differential pressure transducers provide pressure drop measurements across various height locations of the bed. To date, tests have been performed using AIChE ID50 particles at temperatures up to 450 C and superficial gas velocities up to 0.55 meters per second. The figure on the left demonstrates average particle volume fractions for these tests as a function of temperature and a dimensionless excess gas velocity denoted as U hat. As expected, we observed decreasing particle volume fraction with increasing temperature and gas velocity. Nonetheless, over the full operating temperature range, we maintain relatively high particle volume fractions, which is expected to be beneficial for achieving effective heat transfer. Here I show measured heat transfer coefficients for the same set of tests. We see that heat transfer increases with increasing temperature due to the corresponding increase in the thermal conductivity of the gas, and at higher temperatures, the increased contribution of radiative heat transfer. Interestingly, we observe a peak in heat transfer at intermediate gas flow rates. At conditions expected for particle SiO2 heat exchangers, this maxima corresponds to quite low gas utilization, with gas to particle mass flow rate ratios less than 2%. From these data, we construct a new heat transfer correlation. We quantify the radiative component, treating the particles and wall as gray surfaces with relative U factors of 1. The particle convective component is fit with a Nusselt number correlation that follows the general form used by Molaris. The Nusselt number is modified by 1 plus the inverse of a two-phase Prandtl number and is fit as functions of U hat and the laminar Archimedes number. Various functional forms are considered and fit to the data using a nonlinear least squares fit solver. The resulting correlation is shown at the top. The functionality with respect to the laminar Archimedes number is a simple power law relationship, and the U hat functionality follows the general gamma distribution. The figure on the left shows our correlation plotted alongside the experimental data, and the figure on the right plots the correlation prediction with respect to the measured heat transfer data at the same condition. The solid black line denotes perfect agreement between the correlation and experimental measurements, and the red dashed line denotes deviation of plus or minus 10%. While the presented correlation is preliminary and is being updated as we collect additional data, it is encouraging that the current approach captures all experimental data to date within plus or minus 10%. These data are being used to inform the design of a prototype 40 kilowatt heat exchanger that is to be fabricated and tested at Sandia's SCO2 test loop. The heat exchanger will comprise a bank of narrow channel fluidized beds separated by diffusion bonded plates with microchannels for counterflowing SCO2. The prototype will be constructed of stainless steel, limiting the maximum operating temperature to 620 degrees C. To explore design and operation trade-offs with respect to heat exchanger performance, a steady-state, one-dimensional model has been implemented in MATLAB. An illustration of the modeling approach and geometry is shown to the right. The model is vertically discretized and couples a two-phase fluidized bed submodel to microchannel SCO2 flows via wall boundary conditions with conduction through interstitial confining walls. Mass momentum and energy conservation equations are solved simultaneously to determine state variable profiles for the particles, fluidizing gas, SCO2, and stainless steel walls. The baseline geometric and operating parameters are shown on the left and were selected based on a simple thermodynamic model of the heat exchanger design. The results shown here demonstrate trends in particle-to-wall and overall heat transfer coefficients, heat recovery effectiveness, and overall heat transfer with respect to two varying design parameters, bed depth and fluidizing gas-to-particle mass flow ratio. The results indicate optimal bed depths with gas-particle mass flow ratio pairs to maximize heat transfer. These optimal pairs correspond to the maximum in heat transfer at intermediate gas velocities shown before, with gas velocities increasing with decreased bed depth and increasing mass flow ratio. Along that heat transfer optimal line, heat recovery effectiveness and overall heat transfer increase with decreasing bed depth as less fluidizing gas is required to achieve the gas velocity that maximizes heat transfer. Improved fabrication technologies by our partners Carboceramics has the potential to enable the production of smooth, high-density spherical particles with near monodispersed diameters down to 160 microns. Furthermore, fabrication with high-performance nickel alloys permits particle inlet temperatures approaching 800 degrees C. To explore the impact of these developments, model results were acquired with varying particle size and inlet temperature. Decreasing particle size and increasing inlet temperature provide monatomic improvements in all performance metrics, with particle size dominating the impact on heat transfer coefficients and heat exchanger effectiveness, and inlet temperature dominating the influence of overall heat transfer. The results indicate that target particle wall heat transfer coefficients of 1,000 watts per meter squared Kelvin and the corresponding overall heat transfer of 650 watts per meter squared Kelvin are achievable with greater than 90% heat recovery effectiveness when using particles smaller than 200 microns and inlet temperatures greater than 600 C. In conclusion, we have established a new test facility for investigating the impact of bed operation and particle properties on heat transfer and fluidization in a narrow channel fluidized bed. We have demonstrated particle-to-wall heat transfer up to 750 watts per meter squared Kelvin with particle volume fractions greater than 0.45. From our experimental data, we derived a new heat transfer correlation that matched our data within plus or minus 10%. We developed a steady-state one-dimensional model of the heat exchanger, and using that model project overall heat transfer coefficients greater than 650 watts per meter squared Kelvin, more than twice that generally observed with moving packed bed designs, with heat recovery effectivenesses greater than 90% when using particle diameters smaller than 200 microns and inlet temperatures above 600 C. These results suggest that narrow channel fluidized beds could enable the development of smaller, more cost-effective heat exchangers for coupling CSP to high-efficiency SCO2 power cycles. Future work includes expanded heat transfer testing with additional particles up to 600 to 700 degrees C. Continuing ongoing work developing a techno-economic multivariable optimization model of a pilot-scale plant to select preferred designs and optimization to minimize the levelized cost of electricity. And finally, as a critical next step in validating this approach, fabricating and testing a demonstration 40 kilowatt heat exchanger at Sandia's SCO2 test loop. I would like to acknowledge the organizations and individuals listed here for their support of this work.